To finish this lesson, we're going to now talk about inverse functions. First, recall what the vertical line test says. It says that if you have some graph on the Cartesian plane, then that graph is a graph of an actual function if and only if no vertical line intersects the graph more than once. So, for example, real quick, something like that would be the graph of a function, because if you imagine vertical lines, no vertical line is gonna cross this graph more than once. Now imagine no matter where you draw a vertical line is not gonna cross this graph more than once. Just once here, again, it doesn't matter. What I drew here, this black graph is the graph of an actual function. But something like this, something like that, let me see, like a circle, that cannot be the graph of an actual function, because if I draw a vertical line, that's going to intersect the graph more than once. Here is one time, here is the second time. So that violates the vertical test. That means this is not the graph of an actual function. This is, but this is not. Okay, so that's a quick review of the vertical line test. So it turns out there is such a thing as a horizontal line test, but it is not for the same purpose. It's something entirely different, and we're going to talk about that test in a minute. It is used for another purpose, and they're not related, okay? But before we talk about what the horizontal line test is for, we have to introduce some definition, a concept first. So, so this concept is the concept of what is an injective or one-to-one function. So the word one-to-one or injective are synonyms. They mean exactly the same thing. And usually college algebra textbooks like using the word one-to-one. I like using the word injective. I kind of like it better. But injective and one-to-one mean exactly the same thing. Okay, but again, you will probably see this more often at the college algebra level. In more advanced math classes, you usually use the word injective. It's a synonym. They mean the same thing. Okay, so what is a one-to-one or or injective function? Well, an injective function is just going to be a function that satisfies the following property. Whenever you have two different inputs, the outputs have to be also different. Or in other words, and using the contrapositive, which is like a logical way of rephrasing things, of rephrasing statements, equivalently, if you start with two outputs that are exactly the same, that means the inputs must have been the same. So in terms of, if you remember the old way of, one of the basic ways of representing functions using arrows. Um, so suppose this is A, this is B, and this is my function f. So whenever I start with two different inputs, then the corresponding outputs must be also different. So let's say I have these two inputs. They're different, right? So that means their outputs, whatever they happen to be, need to be different as well. I don't know what they are. Let's make something up. Let's say this one goes here and that one goes there. So this is the output of that. That's the output of that. So the outputs are different. And that one, they're different inputs. So their outputs have to be different as well. Maybe this one goes here. and the output of this one has to be different if this is injective. So something like this is injective or one-to-one. So basically every arrow goes to a different spot. Now I can make another example of something that is not injective. Let me call it something else, maybe G. 1, 2, 3, 4. 1, 2, 3, 4, 5. So let's say you have this one goes here, and let's say this one goes there, and let's say that one goes there, and that one goes there. Okay, so this function is not injective or one-to-one because you have two different inputs that have the same output. Whenever that happens, this function is not injective. So this is not one-to-one or injective. Same thing. Okay, so this is not one-to-one. You cannot have two different inputs that have exactly the same output. If that happens, this is not an injective or one-to-one function. So that is what that means. Okay, um, so let's figure out whether these are one-to-one or injective. Question, are these one-to-one or injective? Well, the easiest way, if you're going to do this algebraically, and we're not going to focus too much on this, but if you're going to do this algebraically, is to do it this way, right here. Is it true that if you assume that f of x equals f of y, where x and y are two inputs, if it's true that you assume that f of x equals f of y, and you simplify this, blah, 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 you simplify. So assuming that you start with this, if you simplify, 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 simplify some more, is it true that you end up with x equals y? If you end up with x equals y after simplifying, then that means that the function is injective. That is usually going to be, if you suspect that the function is injective, if you suspect it is injective, this is usually going to be the easiest way to figure it out. Now, if you suspect that it is not injective, then the easiest way will probably be to come up with an example. An example of two things that are different, but that have the same input. So in other words, the easiest way to disprove that something is not injective is to offer a counterexample. If you suspect it is injective, then algebraically this is the easiest way to figure it out. So we're gonna do a couple of examples. We're not gonna spend too much time on this, but you should see just a few. Okay, so starting with this one. F of x equals 2x. Is this injective? Well, is it true that when you start with two different things, two different numbers, when you plug them in, you get two different outputs? Let's say, for example, 5 and 7. 5 and 7 are different. When you plug them in, do you get different things? Like, if you plug in 5, you get 10. If you plug in 7, you get 14. So those are different. So how about you try another pair, like 1 and 10. If you plug in 1, you get 2. If you plug in 10, you get 20, which are different. So, and then you try a few more, you think, okay, it seems like whenever I plug in different numbers, I get different answers. So maybe you start suspecting that this is injective. And it is. Now, since we suspect it is injective, the easiest way to remove all doubt is to do this. Is it true that when we start assuming that f of x equals y, when I simplify this thing, simplify as much as you can, Is it true that I end up with x equals y? Let's see. If I start with this, well, f of x equals 2x, and if I plug in y, I get 2y. Okay, now I can divide both sides by 2 to simplify things a little bit. And I end up with x equals y. It works. So that means indeed, every time I plug in two different numbers, I'm always going to get two different outputs. So this is indeed injective or one-to-one. This is injective. Now, how about this one? Is it true that whenever you plug in two different numbers, you always get two different answers? Can you think of two different numbers that when you plug them in, you get the same answer? This one is actually not injective. You can think of two numbers that are different, two different inputs that have the same output. For example, if you plug in -1, you get -1 squared, which is 1. If you plug in +1, you get also 1. So there's two different numbers, but they have the same output. You have two different inputs that have the same output. That cannot happen. That can happen if the function is injective. So that means this is not one-to-one or injective. This is not injective. Okay, this is not injective. Because we found two different numbers that have the same the same output. Okay, how about this one? Try to think about that one. Is that injective or not? Okay, this is also not injective for exactly the same reason. And I can even use the same numbers. If you plug in -1, you get absolute value of -1, which is 1. If you plug in 1, you get absolute value of 1, which is 1. So again, we found two numbers, two different inputs that have exactly the same output. So that means this is not injective. That cannot happen. If that happens, this is not injective. Okay, and lastly, f of x equals x plus 1. Is this injective, yes or no? If you think it is not injective, then you should be able to think of two different numbers that when you plug them in, you get the same thing. Two different numbers that when you plug them in, you get the same thing. And after you try and try and try, you really cannot come up with two different numbers that when you plug them in, you get different things. The same thing. So for example, if you come up with 1 and 5, when you plug in 1, you get 2. When you plug in 1 here, you get 2. When you plug in 5, you get 6. And no matter what two different numbers you plug in, if you plug in two different numbers, you're always going to get a different answer. So you might suspect that this is actually injective. And it is, but to remove all doubt, this is the way you check. So is it true that when we start by assuming that f of x equals f of y, and we simplify this as much as possible, do we end up with x equals y? And well, let's see. F of x will be x plus 1. When you plug in y, you get y plus 1. And then you can subtract 1 from both sides, and you end up with x equals y. So indeed, if you start with f of x equals f of y, and you simplify as much as possible, you do end up with x equals y. It is true. So that means this is injective. Okay. If you have the graph or you can visualize the graph, there's a much easier way of figuring out whether something is injective or not, and it is by using the horizontal line test. Basically, the horizontal line test says um, says that a function is injective or one-to-one if and only if every horizontal line through the graph intersects the graph in at most one point. So it's like the vertical test, but not with horizontal lines. So a horizontal line cannot intersect the graph more than once. If it intersects the graph more than once, then it is not injective. And why is that? Well, if you have a graph and you have a horizontal line and it intersects the graph at more than one point, let's say 2, could be 3 or 4 or more, but at least 2, then that means you actually have indeed two numbers. Let's make something up. Let's suppose this is -2 and this is like 2. I don't know. Then you would have indeed two different numbers that when you plug them in, you get the same output because the x values are the inputs and the y values are the outputs. So you would have two different numbers, two different points that have exactly the same y coordinate, and the y coordinate is the output. So whatever that is, I don't know, 3. Let's say it's 3. So they have the same height, so that means they have the same output. And that cannot happen. You cannot have two different inputs that have the same output. So, and that is the same as saying that this horizontal line cuts the graph in two different points. So that's how you can visually figure out real quick by just looking at the graph if a function is injective or not. And it turns out we could have figured out all of these examples just like that in like 3 seconds if we can think of what the graphs of these things are, which is a way at least I want you to know how to do these problems for the most part. Because these are all basic functions you should be familiar with. You should be able to look at these formulas and think of what the graph of that looks like. So let's go over all of them. That's what examples 9 is about. So we don't really have to write much of anything here, but draw some quick sketches. So for A, if you look at that, you should be able to immediately think of the graph of this, which is a line. That is a graph of a line. There's a linear function. So for A, and actually the slope is positive, so that means it rises instead of falls. So the graph of this could be something like that. Don't worry too much about it, just worry about just the general shape of the graph. So you don't have to draw a perfect graph for this to figure out whether it's injective or not. So just have a visual in your mind of what the graph looks like. Indeed, it is a line. It looks like that, a line that rises. If you imagine now the horizontal line test, there's any horizontal line will never intersect the graph at more than one point. So this is indeed injective because it passes the horizontal line test. Now let's look at the next one. That is a parabola. That is the basic parabola that opens upward. This is one of the Tolkien functions, and it's also the parabola we discussed moments ago. So the graph of B looks like that. If you imagine, if you apply the horizontal line test, then this fails miserably. There you have a horizontal line that crosses the graph at two different points. So this is not injective. It fails the horizontal line test. This is not injective. Now let's do C. What does the graph of that look like? That's the absolute value function. We should have a visual of that without looking it up. It looks like a V. Aha. So similar to this, it fails the horizontal line test. Fails the horizontal line test. So that means this is not injective. And lastly, what is the graph of that? That is another line that rises just like A. Is actually shifted up by 1. So if you want to be like accurate, up is like this one shifted up by 1. But that's not terribly important to figure out whether it's injective or not. So you have the visual, okay, that's it. That's good enough. And that is injective because it passes the horizontal line test. Imagine horizontal lines, it doesn't violate the horizontal line test. So this is a quicker way of figuring out whether a function is injective or not. Okay. Okay, now let's talk about what's the big deal with uh, injective functions. Well, injective functions are important because these functions are precisely the ones for which the effect or the relationship of input-output can be undone or reversed. So these are the functions for which if you give me the output, I can figure out what was the original input. If you give me the output, I can tell you without any doubt whatsoever what was the original input. So for example, if this was my graph, my function, if you told me that the output is this, then but if I know what the function is, I would have no doubt in my mind that the input was that. If you told me that the output was this, I could tell you that the input was that. However, if the function is not one-to-one, such as this one, and you tell me that the output is this, then I could not tell you what the input was because it could have been X, this one, or it could have been this one. Why? If you all you do is tell me the output, there's no way for me to figure out which was the original input because they both give me the same output. I would need more information, but you don't need more information if the function is injective because for each output there is a unique input. So that means this one you can trace your steps backwards and go from output to input if it is injective. But if it is not injective, then you cannot do that. You cannot tell me what was the original input if all I know is the output. For a concrete example, you can think of um, this function: f of x equals x squared. If that is my function, okay, if all I tell you is that the output is 4, Can you tell me what was the original input? What was the number that I originally thought of to put in here to get 4? Well, if you say x equals 2, well, that is one possibility, but it is not the only possibility, because I could have also put -2 in there, plug in -2, and still get the same answer as 4. So there's no way for you to tell me, for anybody to tell me, uh, if I'm thinking of a particular input, one of these two, to tell me without any doubt that I was thinking of this one or I was thinking of the other one. I could have been thinking of either one. So there's no way to figure out what was the original input if all I know is the output. So this is not injective. So that's kind of important. If an important property for a function to have, you can undo things. You can trace your steps backwards. That's also always a nice thing to be able to do. Okay, so those functions then that are one-to-one or injective, you can undo this. And you can undo it actually by means of another function, which is called the inverse function. So the inverse function is another function called the inverse function of f, and you denote it with f inverse. That undoes everything. So if you start with the output and you apply f inverse, you get the original input. And you can think of it as one function undoes the other one, so they kind of cancel each other. So you see f inverse composed with f cancel each other, and you end up with just x. Or if you put in the reverse order, um, f and f inverse cancel each other. And that's true as long as uh, the range, as there's no gaps, as long as there are no gaps. And I'm not going to get too technical, but something like this shouldn't happen. So that means everything is taken care of. So there's the different outputs, by the way. So there's no like things left hanging. All right, so we're not going to worry too about that, but assuming that that the that the codomain is the same as the range, the set of all possible outputs is exactly the same thing as the set of all outputs. A function and its inverse cancel each other off. Okay, one function undoes the other one. They're reverses of each other. And this notation that you see here, f inverse, that's f inverse. We use a notation, the same notation as an exponent. We write it like this, but that's not an exponent, okay? Don't ever confuse that. That is not an exponent. It's just a notation for the function f. This is not an exponent, okay? So this is writing this. That does not mean 1 over f of x. Or writing this, that does not mean f of x to the -1. Writing that does not mean f of x to the -1. None of that is true. This is not an exponent right here. When you write it right after the f, that just means the inverse function, the function that does the opposite. All right, finding the inverse function is not particularly difficult. There's a few steps, but these steps work for all functions, regardless of what the original function looks like. And there's 4 steps. You don't have to worry too much about step 1. Step 1 is basically figure out whether the function is one-to-one or injective first. So because if it is one-to-one, if it is injective, then it's going to have an inverse function. If it is not injective, it's not going to have an inverse function. So what are you looking for, right? So step one is like, does the function really have an inverse function? So assuming that it does, okay, you can then start with step two. Then you're going to, first thing you're going to do is you're going to replace f of x with y. That's going to make things easier. This is not absolutely essential, but I mean, you should really do it because it makes things easier to read and figure out. So instead of writing f of x, you're going to write y. And this is only done with the intention of making the notation algebraic manipulations easier. Then you're going to swap the x and the y. Wherever you see x, you're going to put in y, and wherever you see y, you're going to write x. So you're going to interchange them. And the reason we do this is because the inverse function actually reverses things. Okay, we're looking for the inverse function, so the inverse function is going to reverse things. So we should reverse the x and the y, swap them. And then we're going to solve for y. We're going to solve for y, and then we're going to get a formula for y equals whatever. I don't know, make something up. Then that formula that you get, that whatever, is the formula for the f inverse. And then that would be it. Okay? So that's how you do it. As long as you don't make any mistakes, you don't really have to double check your work, but you could check your work by you could check your work if you wanted to by composing the f inverse that you found with the original function and simplify and see whether you get x, and you would have to do it with both sides. That's too much work. Just make sure you don't make any mistakes. But it's true, it's one way of double checking. Okay, so let's find the inverse function of this. This is a linear function. Um, it looks like this. Okay, this passes the horizontal line test. It is injective. It is going to have an inverse. Okay, let's find the inverse function of this. So step one is, okay, I already know that it's going to have an inverse. The very first actual step after I know that it has an inverse is we're going to write, instead of f of x, I'm going to write y. So this is going to be y equals 3x minus 5. Instead of f of x, write y. So then the whole thing looks like y equals 3x minus 5. Then you're going to replace the x with y's and the y's with x. So you're going to swap the x and the y. I'm going to swap the x and the y. So this is going to look like this. X equals 3y minus 5. So first step is write y instead of f of x. Next step is swap the x and the y's. Wherever you see x, write y. Wherever you see y, write x. After you do that, you're going to solve for y. Now I want to solve for y. Once I solve for y, I'm done. That's my answer. So let's solve for y. So I need the y all by itself. So add 5 on both sides. So this is going to be, or just like think of moving it to the other side. This is going to be x plus y, x plus 5 equals 3y. And then finally, to get the y all by itself, divide by 3. So I'm going to get x plus 5 divided by 3 equals y. So this thing that I found here, that's my formula for the f inverse. So then we can write down the answer. F inverse of x equals x plus 5 over 3. Okay, and that's it. That is it. You could write the answer like this if you want. 1/3 x plus 5/3. Same thing. Okay, it's all the same thing. My math I should accept it. Or whatever online system we use in the future. Um, okay, yeah, this should not be any problem. That's it. So, going over the steps real quick. Replace f of x with y, then swap the x and the y's, and then solve for y. Once you solve for y, that expression in terms of x is the formula for the f inverse. Okay, so that's it. Really, there's not a lot to do. Just 3 steps. Okay, let's find the inverse of this one. Another example. Find the inverse function of f of x equals cubic root of 4x plus 1. Okay, so first step is we don't know, you don't, again, as I said, you don't have to worry about. If I tell you find the inverse function, is because I'm already telling you that the function is 1 to 1. You can assume that. If I'm telling you find the inverse function, that means the function is 1 to 1. It's going to have an inverse function. So starting then in the process of finding the actual inverse function, first thing you do is instead of writing f of x, you write y. So y equals cubic root of 4x plus 1. Okay. Then the next step is you're going to swap the x and the y's. This is going to be x equals cubic root of 4y plus 1. And then we're going to solve for y. Okay, y is inside that cubic root, so we need to get rid of the cubic root first before we can start moving things around. Get rid of that cubic root. How do you undo a cubic root? Well, you do the opposite of a cubic root, which is cube. You have to cube on both sides. So that means cube, and then when you cube, so you do it like this. You put cube on both sides. So this is like x. Put cube on both sides. This cube and the cubic root function cancel each other, so they're like inverse functions actually. Uh, that's now that I've been talking about inverse functions. That's the correct way to say it. They're inverse functions of each other. So when you put them back to back like that, when you compose them, they cancel each other and give back what is inside. That is exactly what's going on here. So uh, the cubic root and the cubic functions are inverses of each other, so they cancel each other and give you back what is inside. So this is going to be x cubed equals 4y plus 1. Now, again, I'm continuing to solve for y. Subtract 1. X cubed minus 1 equals 4y. And divide by 4. So x cubed minus 1 divided by 4 equals y. And this expression in terms of x is the formula for the inverse function. So the inverse function of f equals x cubed minus 1 all that over 4. Now one more example to solidify the process in your mind. You can try this one if you would like. You can stop the video and try it. I left this one for last because the algebra is a little bit more involved, but the procedure, the steps are actually the same. They don't really change. Okay, first thing is, right, instead of f of x, we're going to write y. So we're going to write y equals 2x plus 1 over x plus 5. Replace y with f of x with y. Then we're going to swap the x and the y. So this is going to look like this. X equals 2y plus 1 over y plus 5. And now we need to solve for y. Now to solve for y here, you can either multiply both sides by y plus 5, or you can think of this as x over 1 and cross multiply. It's really the same thing. Either way you think about it, it's the same thing. So if you want to think about it like this, x instead of x over 1, you cross multiply, you get x times y plus 5 equals 1 times 2y plus 1. So really you get x times y plus 5 equals 2y plus 1. Either way you want to think about it, that's what you get. Alright, now we need the y. So that means we need all the y's on the same side, everything that doesn't have a y on the other side. But before we put all the y's together on the same side, we need to get this y that is trapped here in these parentheses out of there. So to get it out of there, we need to distribute. So this is going to be xy plus 5x equals 2y plus 1. And now I need all the y's together on the same spot. So this is xy minus 2y. So move this here and then move that over there. Negative 5x plus 1, or just 1 minus 5x. Same thing. And now, what do you think we should do to get the y all by itself? If you said factor out the y, you are correct. Factor out the y because it is repeated. You get x minus y, parentheses x minus 2 equals negative 5x plus 1. And lastly, divide by this because I want the y all by itself. I need to get rid of that. So divide by that and you get negative 5x plus 1 over x minus 2. And that's the answer. That is the formula for the inverse function. So let's write it out. Negative 5x plus 1 over x minus 2. That's it. Okay. The last comment for this lesson is what do the graphs of inverse functions in general look like? Well, the graph of an inverse function is really going to be a mirror image of the graph of the original function. The graph of an inverse function is actually identical, except is a mirror image through a specific line, namely the line y equals x. So for example, let's say I have this function right here, the black one, this one. This function, if you look at that, that passes the horizontal line test. It is injective and is going to have an inverse function. So the graph of the inverse function is exactly the same, but is a mirror image. So it's going to be, you draw the line y equals x, which is this one right here that is in gray and dotted. Y equals x. and you're going to reflect your graph through this line, and then the mirror image of that, the reflection, is the graph of f inverse of x. And that is the relation between a function, the graph of a function, and the graph of its inverse function. The graphs are really the same, but one is a reflection of the other. Okay, through this line. So just imagine that if I were to fold the paper through that dotted line, either way, one graph would fall on top of the other. If you were to fold the paper through this line, one graph would line up with the other one. Okay, and that's it. If I knew the graph of a function that is injective, I can visualize the graph of, or just draw the graph of the inverse function by just uh, drawing the line y equals x and using that as a line of symmetry. And the mirror image through that line is going to be the graph of f inverse. And that's all. That completes lesson 19.